Hello and welcome back to the stream. If you were here from today in Global Hack Week, feel free to drop a hello. If you're not, also feel free to drop a hello. Today we are going to be doing the Nature of Code Workshop Part 2 on gravitational attraction. And so this is, while it is technically an ongoing series, I like to try to make sure that these workshops are accessible, even if this is the first time that you are dropping in. So we will be, I guess, like doing an overview of everything that we've been doing so far, as well as what it is that we're looking at. But before we do that, let's make sure that we give everybody a chance to check on in. Um, so right over here, we have the ability for you to get credit for tuning into this workshop. And so I've just dropped a link in chat, and it's also available in the QR code right above me. Um, and yeah, okay. So I'll give you all a moment to do that while I keep on yapping. Um, there was something I wanted to bring up. I don't remember what it was. Oh, so I actually just found out how to change the virtual background for the stream. So you can see back here, I got a little Star Wars reference out here. 'Cause I think it's fun to um, take advantage of all of the fantasy that exists in the theme of what it is that we're doing today with gravity and space and all those good things. I'm seeing a comment about the complicated things. Yeah, it is a little bit complicated, but I think this textbook does a pretty good job of making it accessible. And if it's complicated to you, it is honestly a little complicated to me too. But that's okay. We're going to be going through it line by line and make sure we understand what's going on. And if once again, if you haven't, I guess, like been to the other workshops, we will get caught up together. Okay, so you may notice that I actually have an Instagram tab open. I believe I'm not signed in, yeah. Um, but I found this pretty funny skit where basically the author is saying that physics is just F equals ma. If you're not familiar, this is, I guess, Newton's famous law of physics. um, where force is equal to mass times acceleration. And I found it funny that this post just shared that basically like there's all these like really fancy looking formulas, which is just the application of F equals ma in different contexts. I thought that was pretty cool. Um, Especially when you see how fancy like these words are. Um, So yeah, if you're interested, I'm going to drop that Instagram reel down here if you want to see that. Maybe give that person a follow. But yeah, today we're going to be playing around with gravitational attraction. This is one of the things that we'll be understanding how it's built. And while we won't be, I guess, like recreating this example, we are going to be going through the exercises in the textbook. Yes, thank you. This guy physics. Unfortunately, I'm not amazing at physics, and I am grateful that there is people who actually remember physics. Um, Ironically enough, let's see, I'm pretty sure that Newton's laws of physics get introduced very explicitly in this textbook earlier on in this chapter, which we have covered on the stream before. Um, I'm just very bad at remembering which law is which number. Probably a good thing that I don't interact with, I guess like do physics calculations explicitly in my day to day. Um, so yeah, the format that we did last stream that I think we're going to continue doing is I'm going to have up the example and we're going to work through this code example and then look to the textbook to see if there's any, I guess, like context that we might be missing and just so that we can practice our code comprehension abilities. Uh, while I know that there's, I guess we're not going to be getting as much retention as far as understanding the actual physics goes, I'm going to leave that to you to go through the textbook more thoroughly. Um, there are also excellent videos that the author of this book has created, available at the title of each, at the chapter heading for each heading within the textbook. Uh, Basically, the author of this Nature of Code textbook is a professor, and he has his own YouTube channel. I think he has excellent videos. And this stream is an alternative way to enjoy his book by, I guess, like actually going through the exercises together. So the emphasis is not on the content, but actually on delivering the exercises within this stream. Okay, so before we really get into building this, I'm going to bring up this living whiteboard that we've been working through. I like to always start with this because this helps me with orientation, and this is something that was confusing to me, so I want to make sure that we always cover this. Basically, um, the program that we're going to be using is a glorified like website text editor. Well, it's not really glorified, but it is basically um, we're using a animation library that is called P5, and it's made by some wonderful folks. The P5JS. It's made by an organization that's called Processing, and they like to, or this library is an up for building art programmatically, and it's good for anybody. So I like it a lot. And one of the reasons why I like it is because at its heart, it's just a JavaScript library. So if you're trying to learn JavaScript, you can learn a lot of JavaScript through this, and all of the JavaScript things that's work in JavaScript also work within P5, since this is just a library within it. This is something that we built yesterday. We built a drag force um, simulation kind of deal. Now it's not a perfect simulation, mind you, but it is an approximation. Now I'm going to do a quick tour of the P5 editor, and then I'm going to go back to my whiteboard. I need to really make sure I have um, a better, more standard way of introducing everything. I always change this up. So yeah, as I mentioned before, the P5 editor basically just takes HTML, CSS, and JavaScript and bundles it up and puts the focus on building the, I guess, like these JavaScript code. So over here, we've got a index.html file, and this is just like a normal HTML file. It's got even less than normal websites would have. All it has is just within the head is a script to the P5 library, and then a link to a CSS style sheet, which is just resetting. It's a CSS reset to make sure that um, I guess that this actually properly sits nice and flush against the top left corner of this screen. Um, and then we've got a couple of scripts that link to some JavaScript files, which we will be going through in just a bit. Let's see. Since this is just a library, if you prefer to program in a different text editor like Visual Studio Code, and you want to do that locally, you are more than welcome to do that. I forgot to show you all how to do that yesterday, but you can just go over here to download, and then you'll be able to download this whole thing as a zip file, and then open it up in your editor of choice. And then if you choose to do any like AI-assisted programming, that's probably going to be the way that you want to do it. But here on the stream, we like to do things by hand. So we're going to continue doing that. I also like to log in. I've just logged in with my GitHub account. That way I have access to all of the previous things that I've built. And so here's a whole bunch of them. Um, okay, so let's see. Next thing is let's talk about the coordinate system. If you remember from your math classes or physics classes, or I guess just like classes outside of programming, you may be familiar with plotting I guess like your graphs on an X and Y axis, where X goes from left to right and Y goes from bottom to top. This is the way that we're pretty used to, I guess, like learning math. Um, Something to keep in mind is that computers actually have the Y flipped around. As Y gets bigger, it actually goes further downstream. And the reason why is because, well, I'm not really sure why we even have it so that Y goes up. conventionally. Like, I don't know why that's the standard, but for computers, the reason why as y increases, it goes further down is because that's the way that I guess like websites are built. We typically scroll from the top going down, and so the one thing that is always certain when we have a website is where the top is. And so, um, like for example, if I were to um, hello. If I were to just start typing words in right here, and just putting new lines and such, it always starts from the top and goes down. And so that's the reason why for computers, when we draw things, the coordinate system, at least for websites, at least, the coordinate system has the y flipped in the other direction. And so if we want to go further down, just make sure the y is going up. Something else to keep in mind is that, and this is common in a lot of animation libraries, when you draw shapes, some shapes will have, or different shapes will have different points of origin. And so what I mean by, I guess, like points of origin, it's kind of like an anchor point. Maybe I should have just described it as an anchor point, where basically it's the frame of reference for that given object. So for a rectangle, in this library, the rectangles are drawn from the top left corner, and then everything else just gets built around that. And then so for a circle though, circles within this library at least, they are built from the middle, and then going outwards. They're defined by a radius. And so if we want to make sure that something doesn't escape the bounds of the screen, we want to make sure that we factor in the radius for a circle. But for a rectangle, we might, if it's the top bound of the screen, we would only need to make sure that the top left corner doesn't leave the screen. And then everything relative to that. And then the rest of this stuff is not super relevant right now. I will bring it back if when the time comes. But for now, let's actually start looking into the code to try to understand what's going on here. So the way that P5 as a library works is we generally look at, or I think of the way a lot of programming languages work is they have a usually one file that's called the driver file or like the driver code. And that is the thing that runs everything else. And then everything else is just kind of like descriptions of functions, which is reusable code statements. And so if we pop over to sketch.js, this is actually going to be the one that is most relevant for us. Um, Usually, we only have two functions, setup and draw. And so setup is a function that runs once at the very beginning, and then draw is a function that runs every frame of the animation, or I guess every frame that the computer is running. And then we've got a few other functions over here. Um, Let me actually show you what the exercise from yesterday, what the driver code for that looks like, just so we have a better frame of reference. Oh, this one also had mouse reset. Let me actually find a better example. Let's do bouncing. Now, if you want to see any of these, I guess like older exercise files that we've been through, you could look through the Discord announcement history, look for wherever it is that I've posted, and then you should be able to see some of these old links. Okay, so here we go. Usually, we only have a setup and a draw function, just like this. But in this case, we have a couple other functions, such as mouse moved, mouse pressed, mouse dragged. These are special functions that are intended to be, I guess, like defined. They're already declared, and so they make it so that they're listening to whenever our mouse does something on the screen. And then we can define what the behavior is whenever this condition is met, such as the mouse being released. Oh, hey, it's good to see you again. Yes, I do remember you. Thank you for tuning in. Missed you yesterday. Okay, so let's keep on going. let's look at the setup function. Nothing too crazy over here. We've got create canvas. Create canvas just means this area that we're drawing right here, where the things that we draw inside of. I guess like, it's setting the area that we can draw, like the size of the paper, if we were thinking about traditional animation. Um, that's basically what that's doing. And we can actually make this more explicit by changing the background color. I like to try to come up with some sort of color that's thematic. So right now, since we're doing like a space themes thing, I was thinking we could do a dark background. Pretty close to black, but maybe not like maybe something that's a bit more bluish. So we'll do something like this. We'll run that. Okay, I can't really see how blue that is. I think that's just because of my monitor though. So we're gonna bump up the blueness, and now it's purple. I actually kind of liked that, I think. But yeah, hopefully you'll be able to see where the edge of the canvas is. My hat was good then. Thanks. You don't like this current hat? I was thinking about wearing a more obnoxious hat today, but I felt like it didn't really fit the theme. If you're curious what the other hat candidate was, I'm gonna go grab that. So I have this wonderful cowboy looking hat that I like to wear for when I'm coaching events, but I haven't really found a reason to wear it on stream yet, and so I just haven't been wearing it. Um, the hat that he's referring to, though, I also have right over here. So this is the hunter cap that I wore last GHW when we were working on this stream. You know, maybe this is thematic, because space is cold. I appreciate the love for hats. Um, okay, where were we? Ah, yes. So we had just finished coloring in our space over here. Maybe we can change the color of the attractor and the mover. Um, but we can't do that out here. Let's make sure we finish understanding what's going on in this driver file. Oh man, I'm really appreciating all of the love for the hats. Thank you, everybody. Someday I'm gonna get some more wild hats. You should see when I put on my beard. I have a beard that I wear sometimes. Not for the love of beards. Well, actually, maybe just for the love of beards. I don't know. When I find a reason, I will bring that on stream. Actually, sorry. Funny aside, I was having a meeting with my advisor. I'm in grad school, and we were in this lab meeting for a project that we're working on. Um, my advisor like suddenly realized that everybody in the meeting had beards except for me, and he was like, "You know what, Ryan? I think I'm sorry, but I think you're gonna need a beard to be on this project." So someday I'm gonna show up with a proper beard and we'll see what he says about that. Yes, I appreciate the enthusiasm for all of the funny dress ups. Okay, let's get back to it, and then maybe we can dress up our planetary action over here to be just as stylish as wearing hats. To be stylish enough to wear hats? I don't know. Okay, so we've got a mover and we've got an attractor. So it seems like these are going to be two different classes we're going to be making. That makes sense because we've got one that behaves very differently than the other, even though they look kind of similar. Okay, now that we're done understanding that, let's take a look at the draw function. We saw that we can change the color of the background just like that. Um, and then we are creating a new force and applying the function attract to it. Okay, so Based off of how we were doing forces from the I guess like previous streams, um, basically a lot of what we're doing involves the use of vectors. If you don't know what a vector is, I present to you vector meme. Vector has both magnitude and direction. This guy's known for it. Um, yeah, so it's basically just something that has a size and a direction. I don't know how else to say that without restating what I just said. Um, Within P5, vectors are defined with an x and a y coordinate at minimum, and those x and y coordinates, um, they can be used as a relative of like points away from the point of origin. And so the point of origin typically within P5 is at 0 and 0, but sometimes you can also set up, I guess, like relative points of origin relative to wherever the object is. And so um, this a vector, I'm assuming, or sorry, this function right over here, I'm assuming is setting up I guess like direction to, or okay, this is the attractor, which is telling the mover and probably setting the mover's, I guess, like heading or direction to move towards wherever the attractor is. And then we set this into a variable force, and then we tell the mover to apply that force, and so it'll start moving in that direction. We'll look at what the apply force thing looks like in a bit. And then we run updates, which basically is the thing that actually crunches the math down to make sure it actually moves. And then we just make sure that we draw them onto the screen right over here. I'm realizing now that all these functions got unhidden. So something else to keep in mind. Um, oh, good call out. Yes, technically, vectors within P5 are defined as an X, Y, and Z. You can do three-dimensional vectors. For um, usually adding in the third dimension complicates the math in a way that is kind of sad. Not sad, but it's kind of spicy and a bit too spicy for what we're trying to focus on, which is just on using physics in general in our animations. So we're not going to be looking at the Y component, but that is a good call out. Thank you for correcting me there. Okay. So as far as animations for computers go, something to keep in mind is that computers fake animation, or I guess like they fake movement. Because in real life, if I every time I like move my hands from one place to like another, my hand actually exists at all of those points in time. If you, I guess like um slice, or if you have a small enough time scale, like if you're looking at like a thousandth of a second, or a thousandth of a second, my hand still exists in all of those, I guess, like fractional parts of time. But for a computer, we don't need to be that accurate, and they don't work in the same time scale, I guess, like in real life. So what I'm trying to say is that we fake movements by looking at where the position should be, and then just doing a simple like math translation. And when I say math translation, I just mean like we just move the objects. So if the object coordinate was supposed to be at, let's say, x is I'm going to move this square, for example. Let's say that it starts at 0, 0, and then so on the next frame, it could be moved to maybe like 2020, which would be like something like this, right? And so, but the thing is that this square it didn't actually needs to be everywhere in between these two locations because our eyes can't see fast enough, at least at the current frame rates that we're working at within this animation. Um, I realize I'm saying a lot more, I guess, like wordy, jargony things this stream than I did yesterday, so I apologize if I'm confusing you. Please feel free to stop me and say, Ryan, you're not making any sense. Can you explain what is going on better? Um, feel free to stop me. Okay, but yeah. Um, let's see. So when I say frame rate, I'm talking about how fast the animation changes on the screen. And so P5 base animation speed is at 60 frames per second. And so if we wanted to move this thing at 60 frames per second between two locations, we can do some math to crunch it. But I guess the important thing that I'm trying to say is that um, we fake movements by just adding, or I guess just like moving the position of our objects by a little bit. This will probably make more sense when we actually look at the update function to see how that works. So I'm going to stop talking about that. And let's just take a look at the rest of these functions over here. Okay, so we've got mouse moved. This uses a handler and just looks at wherever the mouse is. This uses another handler and another handler. Okay, so nothing too crazy to look at there. We will cover that when we look at the attraction functions. For now, let's actually jump into the things that I was yapping about. Okay, you want to say that it can give some problem if the move is too fast. If it is very fast, it can go through walls. Yes, that is a much better example to highlight the problems that I'm thinking about. Um, I wonder if Okay, so since I already have this up, we're going to talk about how the update function works, and then I'm going to highlight this example right here. And this is like if you've done anything with game development at all, this may be a familiar problem to you. I'm sure this is a familiar problem to other fields, but specifically within game development, this is something that happens very often. Um, so before we do that, let's actually just highlight, since the mover isn't too crazy, let's highlight what's going on over here. We've got a few functions going on. This is a class of mover, so if we wanted to create multiple movers, we could just say create new mover with these values. And the constructor class is something that allows you to create said mover with said values. And so each one of these movers comes with a few properties, or I guess like variables that just describe what this object is at a certain point in time. And so we can say that this object's mass is the size of the thing that it puts in here. The radius is going to be 8 times that. And then we've got a position vector, a velocity vector, and an acceleration vector. Okay, so then if we look at apply force, this is just going to, okay, let me take a step back. So vectors, and this was covered in a previous part of the textbook. Vectors, I guess okay. So in a previous part of the textbook, we tried to avoid using, I guess, like any specific classes. Or maybe we did create our own class. I don't actually remember. But we could technically handle everything as independent X and Y values as far as where it is that we drew our, let's see, draw our shapes. And so if we look at the show function, let me actually look at, okay, I keep opening up all these cans of worms, and then without closing some of my old cans, I guess. So within the show function, this is responsible for just drawing our mover object. We've got a few things going on. We've got stroke, which is just going to describe the color of the border around our shape. And so we can't really see it here because it's very dark, but we can bump up the brightness of that. Okay, so yeah, now we can actually see the border around our mover. Stroke weight is just how thick the border is going to be. The fill is the color inside of the shape, and then the circle is, well, the shape of whatever it is that we're looking at. And so if we wanted to change this into a different shape, like a rectangle, we could just turn that into a rectangle like that. and it still has similar things. We're gonna keep it as a circle for now, but maybe we might doll it up later if we're feeling kind of fun. Okay, so then a circle is defined by three things. It's got a position X, so this is how far left and right it is, and then position Y, which is how far down it is, and then we've got the radius, which is how big it is. Okay, so I don't remember what it is that we wanted to explain, describe. Oh, okay. So earlier, previously we had tried doing this without using vectors. And so we could just put in, I guess like instead of this dot position dot x, we could just say like 30. And so you can see here that we could just do that, but the reason why we actually have it attached to a vector instead is because vectors allow us to do matrix multiplication. If you don't know what matrix multiplication is, it's kind of like just doing a box of math, a box of numbers, and I'm going to leave it at that. So there's a lot of, I guess, like mathematical operations that we want to be able to run that we can do with vectors more conveniently if we use a vector object. So the way that we use vector objects is, or create new vector objects is with create vector. Now, previously we had said that vectors have both magnitude and direction, but we can actually kind of describe both of those by just saying where it exists in the world with just the coordinate system. Okay, like attributes or characteristics of the objects. Unfortunately, I've been yapping too much to pay attention. I don't remember what this might be referring to. Feel free to I guess like ask for clarification again. Um, but I believe yes. The answer is yes there. Sounds like quantum physics. I'm not a quantum physics guy. I do not know much about it. But I will say that it is pretty spicy when we get to that. Okay, so now that we know how our circles are drawn with just the position x's and y's, um, and let's actually look at the update function to see how it knows where it's going to be next on the screen. And then we'll look at our quantum physics vibration escaping boundaries kind of situation. So we've got this update function. Um, this is the most important. This is the thing that gets written first. Basically, our position, where the location that our circle gets drawn, right? This is the final product. This thing is literally just adding in where it's currently supposed to be moving. So velocity is just telling it where it should be in the next frame, or like how much it should change by, right? Um, and then acceleration is the thing that tells velocity how much to change by. And so we can just do that by doing dot add. And so the dot add allows us to add to both the x and the y at the same time. And also allows us to do, I guess, like multiplication and like a few other things, or sorry, vectors allow us to do all of that math with a simple dot add instead of having to change the x and the y independently. Okay, so not too much going on over here. That pretty much adheres to what our definition of velocity is. And then we've got something over here that's pretty interesting. And this basically just says this dot acceleration is going to be multiplied by 0. And we know the 0 property of math basically says if it's multiplied by 0, it becomes 0, right? So the reason why we have this is, well, actually, let's just see what happens if we get rid of it. You can see that it just kind of just yeeted out of here. It's like, nope, I see something that I don't like, and so I will leave. So the reason why we need to do that is because otherwise, because the way that forces work, um, force is only applied when, or sorry, acceleration is not necessarily something that's always constant. you only accelerate something as long as force is continually being applied to it. And so the moment that you like, let's say that um, like this hand right here is pushing into this hand. The moment that my hand stops pushing is the moment that the acceleration stops being applied. And so the way that we do that is just by multiplying by 0. So that's something that we need to make sure we do at the end of every frame after we've calculated how far our object has moved. Okay, and then we can look at applying force. So let's see. We do a little uh, vector division on the force divided by the mass. I don't remember exactly why we did that, but that is definitely covered earlier in the chapter. But this is the main thing to know is that this acceleration, or this is how we decide how much an object is being accelerated by. This is how to actually apply the force to the object's current mass, is what I'm trying to say. Okay, cool. So that should describe how movers work. Now, if we want to understand why we can get into this going through wall situation, this is going back to our problem of, I guess, like computers aren't doing things in like in real life. So let's say, for example, um, what's a okay. Let's say for example that the X and the Y are like a wall within this shape, right? And so if we take this box and let's say that the velocity is going, I guess like every time we take a step, this box moves the size of one box. So if the box is right here, then on the next frame, it's going to be right over here, right? Let's actually color this red. We're gonna do a little bit of onion skinning. If you um, are familiar with animation, onion skinning is where you can look at uh, the previous frame and or the next frame of whatever it is that you're looking at while looking at the current frame. And so the next and the previous frames are kind of like they're more opaque, so you can kind of see them. You can get a hint of where it's going to be next, while still focusing on wherever the current frame is. So we're going to say that this is where the next frame is going to be. And so if we were going right by a full one step, then yeah, we're kind of chilling. There's nothing going on over here. But then if we wanted to do, I guess, like a boundary check to make sure that this box doesn't escape into, I guess, like the void, usually what we would do is every frame we would check to see if the box has, I guess, like collided, is touching another object. And so this is fine as long as, I guess, like this next frame isn't inside of another object, right? Whenever the velocity is next going next. But if we have, I guess, like if this object is going fast enough, then I guess to the stage where the box kind of escapes the normal way that we would check to see if it is, I guess, like intersecting with something else. Like, let's say that beyond this X wall, this is supposed to be, I guess, like a solid object, and that this is a solid object. And so we, the way that we might check, I guess, like do a bounds check is we might check to see if this box intersects and like has another body within it, in which case we would then do our like bounce function. But in this case, if the box goes like this, it completely, I guess, like misses this line right here. And so it's effectively just jumps through that wall. Um, I think there's probably a better way of describing that. Yeah, I think I might have lost the plot a little bit. Okay. Basically, I was trying to explain why, I guess like because of how computers fake movements by simply doing math additions to change a position by a set amount. Sometimes, like especially in game development, you can completely bounce through walls. I was trying to describe that. I think I will need to revisit that when I have a better way to describe that. But for now, I just know that that is something that can happen. Okay, let's pop back over here and let's actually start taking a look into the attractor function or the attractor file. All right, so we've got a lot of code over here. Let's just take it one step at a time. So we've got an attractor. This attractor has a few values. It's got position. That makes sense. It needs to exist in the world. It's got mass. That makes sense because we're trying to do gravitational attraction. We've got a drag offset and dragging. I don't know what rollover is, but I'm sure when we find out how it's used, we could take a guess at that. So we've got, well, these two functions is, I'm pretty sure, just for handling the fact that we can move this around. All right, so nothing too crazy over there. Then we've got the attraction method. This is where the, I guess, the heavier stuff is. So let's actually expand this out so we can see this better. So very similar to the mover class, we have a force that's being defined over here, but we actually do a subtraction method. And so the reason why we're doing a subtraction method, I'm guessing, is because we're trying to figure out, I guess, like given the distance between two objects, we want to point in the direction that the other object is. And so we just do a subtraction to find, I guess, like, to make sure that it moves towards the other object instead of moving away from the other object. And then we set a distance to be the magnitude. So the magnitude of the difference between two vectors is just going to be the distance. Well, I think this drawing does it pretty well. This right here is the magnitude of the force because we've just did a little bit of subtraction. And so we're just setting the distance to be equal to that. Now we're going to be constraining it, and the reason why we're going to be constraining it is because of divide by zero errors. And so anytime you divide by zero, that's a technically something that you physically can't or mathematically can't do. You can get like infinitely closer to zero, but you can't like divide by zero. Um, I think there's a really funny a bit where like somebody asked Siri how to explain why you can't divide by zero, and it's talking about how you can't share a cookie between zero friends if you well don't have any friends, and so the bit becomes like kind of a paradox. Okay, yapping aside, I'm seeing we have some questions. I have no idea what Global Hack Week data means. What do we have to do? So Global Hack Week has themes um every month, and so week's sorry, this month's theme is data. And so that means a lot of the workshops and a lot of the challenges are going to be themed around data. I like to also just like continue running this stream every Global Hack Week, regardless of what the theme is. I do think that, well, if you want to, you can squeeze data into this specific topic, but that's not the focus of what we're doing here. Boop, 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 boop. Okay, I just answered that question. Oh, okay, yeah. I see we have the same question repeated a few times. Hopefully that answers your question. If you have more question, if that didn't, feel free to let me know. All right, let's keep on going. So constrain is just going to make sure that our distance sits between 5 and 25 instead of so that we avoid accidentally dividing by zero and causing a problem. I guess if we want to, we can just very quickly just divide this by zero and just see what happens. So we get an error over here, but technically speaking, this still runs, which is really interesting. I'm guessing there might be like a built-in something that was able to. I'm guessing that the P5 library had something to handle the case of a divide by zero error, and it just rounded up to like a very large number. Um, okay, so let's see. This strength function right here, I believe is the actual equation that's calculated right here. This is the force of gravity, which is the gravity constant g times the mass of the first object times the mass of the second object divided by the distance squared, which in this case is r. Over here, it's r, but in our current simulation, it is distance. And then we have a vector r, which is just the direction that we're looking at. And so the direction, I guess like r with the pointy hat, is actually defined right over here where it says force. And so we already have this. And so then we are setting the strength of which it is moving in that direction to be the rest of this equation right over here. Okay. What do we have to do? What are our responsibilities? Quackers and Cheese has that right. Um, yeah, so GHW is very much a do what you want. And if you, I guess, like prove that you've done some of these things, then you get credit for doing it. And so the GHW website is going to be your best source for looking at all of this information. And so Quackers and Cheese has already very helpfully shared the information for what's going on this week. So yeah, after you register, there's going to be a place for you to submit challenges. Let's see, I don't remember if it's actually there. I like to just pop over here and then just click on the hamburger menu, go to challenges. This is where you actually submit things. There we go. So if you want to get credit for checking into workshops like this, um, you only need to attend, I think, like 5 workshops to get the full swag packet. The QR code is right above me. It is also posted in the Discord announcements. Okay. It tends to infinity because if you divide it by 0.0001, you're doing multiplication. So closer you are to 0, the bigger the number. Usually just gives the maximum value of the number of the machine. You can get maximum velocity or go out to canvas and crash. Yes, I think that's a pretty good explanation of why this didn't actually immediately break when we divided by 0. Um, I think computers do a lot of cheating where they don't actually do things like the way that they necessarily work in real life. Although I guess dividing by 0 in real life is just something that you just can't do. Um, so I think it's fair that it has that behavior where it just roughly says you can't do something, or I guess in this case where it just roughly approximates what you should be doing and gives you a warning. All right, so that is the attraction function. The show function shouldn't be too crazy. This has some condition statements, and that's just to make it so that it's more obvious when we actually have something when it's currently being dragged. So it's more of a user experience thing than a physics animation thing. I'm guessing, I think a roll over is actually whether or not the mouse is hovering over the object. So if we wanted to make this like really bright, like just white, um, whenever it's rolled over. Yeah, there we go. So that's what the rollover function does. Mystery solved there. And then we have the circle, which is the same as it was before. And then we have some things to handle mouse interactions. I don't think there's going to be anything too crazy here, or well, there's a little bit of craziness. I don't think that this is important for us to look at in context of the simulation, because this is really just checking to see. if it is pressed, yep. Um, if we are hovering over it and then we just set whether or not is being hovered over, this dot dragging is equal to false. Cool. This dot drag. Yeah, none of these actually affects the physics whatsoever. So that's not something that we need to worry too much about. It is kind of satisfying to see it kind of run around. Okay, so that is an overview of the code that we're looking at here. Let's pop back over to this textbook. I didn't have any questions about, I guess, what was going on over here, that this sketch itself didn't seem to answer already. So I'm going to scroll over to the exercise and we can get started with that. Acceleration vector. So this is explaining why it does the subtraction thing, I guess. Yeah, because if it was addition, then it would be going in the opposite direction of where the object is. That's actually something that we did in a previous project where we were adding wind force. We wanted to do vector addition since they were moving in the same direction, but since we want them to move closer together, that's when we do a vector subtraction. Okay, this is a lot of explanation, which is wonderful to see. This is the part that handles divide by zero, I think. Here we go. You can't divide a number by zero, and if you divide a number by a tiny number, that's the equivalent of multiplying that number by a very big number, which is what we had that helpful comments in chat describing. This is the actual, I guess, like example that we yoinked over here and then changed the background color for. All right, cool. So now we've got our first exercise 2.11. Adapt example 2.6 to map the mass of the attractor and mover to the area of their respective circles. Um, okay, I need to reread that. Okay. To map the mass of the attractor and mover to the area of their respective circles. Wouldn't this should be this dot mass times 2. I'm not entirely sure. Well, I kind of understand what it's asking. Map to the area, map the mass. So this is just asking us to make it so that the circle gets drawn to be bigger. This dot mass. I'm assuming this is supposed to be a function call, but I can't figure out what that would be. I am going to just reveal this. Oh, square root this dot mass times 2. So I think this is referring to the actual, I guess, like physics formula, where it is. I'm gonna scroll all the way back up for it. This where we have this. Wait, no, there's no square root there. Um, why is there a square root there? To the area of, oh, wait, square roots times 2. Is that because the area of a circle? Diameter of the mover and attractor scaled according to the mass of each object. In the real world, mass and size are related in a bit of a different way. Area of a circle is pi r squared, where r represents the radius. As such, to represent an object's mass proportionately with a circle more accurately, we should take the square root of the mass and scale that as the diameter of the circle. Okay. Yeah, I guess we could do that. So if we go ahead and pop this over, instead of setting it to be, I guess, like the radius separately, we could do this. So I it's so small. Um, okay, so the reason why that uh basically that's just saying that we've been manually setting up the radius to be independent of the mass. And so if we wanted to previously, we could actually make it so that the radius is just arbitrarily just like 100. I just make it really big, um, so that it doesn't actually affect anything. Uh, so the reason why at this point um, we're talking about, I guess, like doing the square root, this is assuming that, I guess, um, the objects are a specific kind of material that has this specific relationship between their mass and the radius. More accurate. Okay. I think there's probably a better way to phrase that, but I'm not going to get hung up on that because I want to move on to the next exercise. So we're going to take a look at attraction with many movers. I would assume that this is pretty much the same exact thing that we had over here, but just with an array to apply an array that's defined within sketch.js to apply or just to have a whole bunch more movers um, basically running around. So if we pop this open over here, move over to sketch.js, we should see that this is pretty similar to this over here. Tractor.show, apply force, update, show for each thing inside. Yeah, it's pretty much the same thing. Ba-ba-da-ba. Whoop. My browser sometimes likes to just leave that drawer open. Oh, did it again. Okay, let's see if this is any better. All right, I think we've accidentally scrolled down too far when doing that. Here we go. Okay, so now for the first exercise. In example 2.7, actually, let's make sure, I want to make sure that we are doing this with the right square roots thing. Hee. Oh, oh, square root this, and then multiply it by 2. And now we have our little itty bitty thing. We're going to do the same thing with the attractor. And I realized that instead of radius, this should be mass. Very small. Actually, I kind of liked it when it was bigger. So we're going to leave it so that the radius doesn't actually affect how big. Okay, we're going to make it so that the attractor is bigger, but that the mover actually does reflect. Okay, there we go. All right, now example 2.7, there's an array of mover objects and one attractor object. Build an example that has an example that has systems of both movers and attractors. What if you make the attractors invisible? Can you make a pattern or design from the trail of objects moving around attractors? There's a system. There's a bunch of mover objects in one attractor that has both movers and attractors. I'm not sure what this statement means. Oh, sorry, I just noticed a couple comments. I think that means if you do 2 times the diameter, you get a times 4 an area. So if you want the same density on all mass, you should do square root, I guess. I think that's a fair interpretation. I appreciate that. Ah, okay. Build an example that has a system of both movers and attractors. So I'm assuming then that it just wants us to have multiple attractors as well as multiple movers. So that shouldn't be too crazy to do. What if you make the attractors invisible? All right, so let's go ahead and just convert this so that we have multiple movers. So what we're going to do first is we're going to set up mover to be an array. And then we're going to do a for loop. Let I is equal to 0. I is less than, let's just say 10 for now. I plus plus. And then we can move all of these right inside. We should maybe move the attractor outside since we only need to show that once. And instead of an individual mover, we're just going to say, mm, well, I don't really want to change all of that at the same time. So what I'm going to do is I'm going to make a new um, current mover is equal to mover I. Let's change this to movers. Okay, there we go. And so this should continue to work. Can't access position movers undefined. Movers I am assuming no. It's because over here we didn't actually create our movers. So let's go ahead and create our movers. Movers I is equal to new mover. We can do a random value. I don't remember if maybe it's just fully random. Yeah, okay, there we go. Random, random, random. Cool. And then we don't need to worry about the attractor. So then this is going to be a random x value. Let's have it start. Let's see. Well, right now our screen is really wide. Let's actually set up the canvas to be a little bit smaller. Set it up to be 480. Okay. I don't know why I ran that and why it didn't break immediately, but I appreciate that it didn't break immediately. Okay, so let's set it up so that the random size can be anywhere from, let's see, the current size is 2 for the mass, which is very small. Let's go ahead and set it up to be anywhere from 2 to be like 100. Okay, so then for the other values, let's try to do for the y. We can do, oh, look at all the tiny little dots. Um, okay, so this started off at 50, which is around like here-ish. So we can make it anywhere from, let's do anywhere from 0 to the current height of the screen, let's say. And then same thing for the other one. So now they can spawn anywhere in the screen, and now we've got random masses from 2 to 100. Okay, cool. That was a lot more satisfying than I was expecting it to be. I think I'm going to change the way that the attractor looks to make it look a little bit more brighter since we have a dark background. So I'm going to pop over here. We're going to change the stroke to be 250. Maybe 220. There we go. Okay, cool. Let's pop back over to sketch.js. So we did indeed get this working for all of the different um, movers, but now we want to be doing this for all of the different attractors as well. So let's take a look at that. So there we go. We have our new mover. Let's actually get rid of this old one right here. Attractor is equal to 0, I is less than. Let's probably not have 10. Let's just have like 3. I plus plus. Um, attractor's I is equal to new attractor. Oh, I think we should make it so that the attractors have a starting location. Because right now they just start in the middle of the screen. So let's actually pass in a X and a Y. X and a Y. There we go. Okay, so now we pass in the attractors, we can give it a location. Well, let's continue doing randoms. And we will make it so that they spawn maybe 1, 2, 3. We have 3 different locations. One in the middle, or yes, sorry, within a range. Okay, maybe instead of doing random, sorry, we're going to put it into thirds, thirds of the screen. So one here, or maybe 1, 2, 3. Okay, so let's do. So then the first thing is we would want it to be the width divided by 3 plus width offset. We're just going to call it that. Let width offset equals 0. And then we're going to add to the width offset plus equals width divided by 3. So that should make it so that it crosses, I guess, like the third of the screen. Actually, no, we would want it to be like a quarter of the screen. Because if we do a third, then that means the first one's going to be like right here, second there, and then the third one's going to be right at the edge of the screen. So if we do it by fourths, then we should have 1, 2, 3, since we're dividing the screen into fourths. Okay, and then so that's just the Y. So let's actually abstract that out um, into something that's a bit more readable like that. And then we're going to set the X to be the height divided by 2. And that's just going to be that. Okay. So then we're also going to need to make sure that after we set up our attractor, that we apply the show function to every single, I guess, like attractor. We also need to make sure that all of this stuff applies to every single attractor, as well as all of these. Oh boy. So this is going to be a little bit of work, but that's okay. We can do this. So let's start by, I guess, hmm, uh, I'm going to leave this inside of this function for now. And then for the force, we are going to need to have all of the attractors working at the same time. So I think this is where we're going to need a nested for loop. So let's do the nested for loop right up here. Let j is equal to 0, j is less than 3, j plus plus. Actually, even better, instead of having these hard-coded numbers, let's actually set that up over here. Um, let's do const um, movers num is equal to, or maybe num movers is equal to 10, const num attractors is equal to 3. Let's move this down over here to inside this nested loop right there. And let's move num movers down over here. That way, if we decide to change this, we can conveniently just do it in one place instead of in multiple places. Okay, so we can't run the function just yet because we're not done. What we're going to need to do next, let's see if I can hide this. Make this a little wider. Okay, so the next thing is we're going to need to move all of these inside our nested for loop. Current mover, boo, boo, boo. We're also going to need the current attractor, which is going to be, let's change this to attractors. Attractors is already set up there. Good. I don't want to look at setup anymore. Current attractor. This is honestly too big of a thing. Um, I think it's just too wide. So we're gonna do this to C mover. C mover. Okay, and then we're gonna do the same thing with C attractor. And then we're gonna pop over here. We're gonna say attractors. And we're gonna set that to J. Okay. Then we're going to just replace everywhere we see attractor with C attractor. And I think that's going to be it for that. Now, as long as we don't touch any of these, I guess like the mouse handlers right now, it should work. So let's just see what happens. There we go. That's so cool. It's kind of like watching like power up abilities like in an animation or something like that. Like you know when characters do like telekinesis, like Magneto from the X-Men is like moving things across the screen. That's the kind of vibe I'm getting right now. That's very satisfying. Can we make the attractors invisible? Sure, let's just hide that. Yeah. Okay. That is really satisfying. All right, so next thing is we should probably actually start setting up all of the rest of these loops and such for the handlers down here. So let's go ahead and do that. Oop, I accidentally did J++. And then we're going to go ahead and copy this over Remember to change this to I. I'm gonna copy this over here. Oh, actually, it's probably better to even to just do it like that. There we go. And then I'm gonna copy this over here, over here, over here. Then we're going to yoink the second half of this to handle press. Yoink these two over here. Just like that. I'm going to copy this, delete that, move over here. There we have mouse dragged, and then stop dragging. It's going to go over here. There we go. Okay, so now if we run this, we should be able to do that. That did not work. A tractor is not defined. Ah, it's because I forgot to put the S right there. Tractors. Okay, well, yeah, there we go. Oh yeah, when Magneto escapes prison, yes, just like that scene. That's what I'm getting out of here. It's so cool. I'm actually really obsessed over this right now. I could probably like if this was a screensaver, I would be staring at this for way longer than I probably should. Actually, like as a random like personal project of mine, I think it would be really cool, or maybe as a personal project for anybody here. Um, One thing I want to do is I want to have like a mini display that I can just load up any P5 animation that I want to just play there as like a wallpaper. It's like a live art thing. Like those like digital camera frames that allow you to just like upload like Google Photos to it or whatever. I think it would be cool to do that for like animations that like do like actual simulations, and then you can have like a little like a little sensor on it so that it could. Because I know that there's Arduino plugins for P5. Let's actually take a peek at that. I think it's under libraries, contribute examples, tutorial, reference, community. Maybe it's under community. Yeah, here we go. Libraries. Um, all libraries. Oh, um, where is it? Where is it? There is one for hardware. Here we go. Oh, nice. I didn't know there was a phone library. That's pretty cool, actually. There's a Bluetooth one, location. Where's one for just Arduinos? Pretty sure there was one for Arduinos. Ah, here we go. Serial server. If you want to connect it to like an Arduino or something. Anyway, um, let's take a look over here. Can we create a pattern or design from the trails of objects moving around attractors? So one thing that we could try doing actually is right now we are drawing over our background so that we can't see the previous animation frames. But one thing that we can do is we can hide the background draw part. And if we do that, we can just get all of the trails. And they're just permanently on the screen now, which is pretty cool. Okay, so I just realized it is 1:20 right now. So we have a thing. Sorry, I don't know. Okay, so basically, there's another workshop that started that's more on theme with the data, I guess like the data theme. It's called the Data Dashboards Workshop. Um, because of a scheduling thing, we accidentally scheduled a workshop in the middle of this one. And I was supposed to mention this about 30 minutes ago that this was going to be happening. So I'm sorry if you're a Twitch streamer and you really wanted to be in Dashboard, but you're not going to be able to see that workshop. You will be able to see it on YouTube whenever that goes live. Um, or I guess like whenever it gets posted after YouTube. But yeah. Anyway, that's something that's happening right now. That's going to be continuing an hour after this current workshop ends. Um, it's just something that happened. I don't know how else to more fluidly say that. I should like it. The only thing with this, I've been having a lot of struggles with this browser where the drawer likes to just hang out outside sometimes and not like disappear again, which is very distracting. Anyway, this looks so ethereal when you leave the trails on. Oh, so cool. Okay. Um, I guess the other thing that we can do, which I don't think we're going to do for this because I want to get through some of the other parts of this chapter, is to be able to draw, I guess, like only the last five parts of wherever this circle was. That way we get a more dramatic trail, like animation trail between each of these things, instead of just permanently having the entirety of the trail being there. Oh, question. So much for the events. Can Pro.LJS be created like interoperability in JavaScript or having an extension? So you may have missed it earlier, but T5 is just a library for JavaScript. In fact, you can see over in index.html, there's this is legit the only library that we're using right now, which is the P5 library. And so if you want to do other things with JavaScript and with P5, you can totally do that. Um, yeah, it's designed to be very accessible, and so it'll run basically anywhere that you can run JavaScript. Okay. Let me know if that answers your question. Otherwise, feel free to ask for clarification, and I'm happy to hop in. All right. So let's look at the next exercise. This chapter isn't suggesting that every good simulation needs gravity. You should be thinking creatively about how to design your own rules using my approach to simulating the gravitational attraction as a model. Example, what happens if you design an attractive force that gets weaker as the objects get closer or stronger as the objects get further apart, or if you design your attractor to attract faraway objects but repel close ones? Hmm. Those are interesting. Um, let's tackle the stronger. Well, okay. So I think the author is saying here that we can, I guess, like make our own rules for our simulation. Um, and so if we wanted to, we can make it so that if they get further apart, the gravity force gets stronger instead. Um, so let's go ahead and try doing that. I don't know how that's going to affect this animation, especially since we have three of them. I think it's going to make a lot of like slingshotty kind of things. I also kind of like the idea of making it so that they get weaker as they get closer, or not that. Actually, I like this other one where we design our attractor to attract faraway objects but then repel close ones. So I think what we're going to try to do, or for this exercise, is we are going to make it so that whenever the object touches the surface of the sphere, we're going to make it so that it kind of bounces away. And let's see if we can do that. Okay, so first things first is we should probably hop over to the attractor since this is the thing that's applying the forces to, I guess, the movers. And so what we would need to do is, well, I don't think we should put it in attract necessarily. I think we should have this in a new function. We're going to call this push away. And so we are only going to call this function whenever, I guess, the objects actually touch, or the movers touch the attractor. So I don't know where that logic should live. We could make it so that that logic lives inside the mover, or maybe we can make it so that this logic lives inside the attraction, where we do a little check to see whether or not it should be attracted. No. Let's look at where attract is being called. It's not in mover. Uh, Attractor dot attract. Okay, I think we should actually put the logic inside attractor then, for wherever we call the push away. So let's actually write down how we would use the push away before we define how push away works. So we're going in here, let distance is equal to be force magnitude. Extreme distances, force. Okay, so we would actually want to handle this for the rest of this. So handle whether to push or to pull. Maybe we'll, instead of calling it push away, we're just going to call it bounce. Okay, so then if mover dot position dot x is let's see, how do we check to see the distance? Well, the distance is right here. Maybe we want to have the distance be a little bit closer. Maybe we'll want this logic actually to be after this. That way we can take advantage of the magnitude. Okay. I need to remove some of these comments because this is very distracting for me. Limiting the distance. Um, yes, I think that's fair. Calculate the magnitude. That's fair. Magnitude times direction. Force vector. Distance between objects. Yep, we know that. Calculate direction of force. Do. Okay. So now what we can do is we can check to see if the distance is less than, I want to say it's going to be, well, the distance is measured between the radius of the um, attractor plus the mover. So then const bounce distance is going to be equal to this dot radius plus mover dot radius. If it is less than the bounce distance, then we're going to make it bounce. So then apply the bounce force. I'm also realizing that we need to make sure that the radius is actually set as a value within both of these. So let's see. This doesn't actually have a radius yet, so let's add that in. And I know we have a radius defined all the way down in our show function, so we're going to go down here and we're going to grab that. this dot radius, let's set that to that, and then we're going to set the radius to be just whatever the mass times 2 is. Okay, and so let's make sure that our mover also has the radius set up. I know we're not using this current radius, so let's go over to here. I'm going to cut that, this dot radius, and then we're going to replace this definition right here. Okay. Now I can't run anything yet because our attractor hasn't finished the bounce logic yet. So the bounce force, we're going to need to make it so that it is more additive. So like subtraction, if vector subtraction makes it so that things move closer together, addition is the thing that makes it bounce away. So we're going to need to actually take we're going to set force to be equal to p5 dot vector dots add this dot position and mover dot position. Let's see if that makes sense. So then the only thing we're changing is the direction. The strength is going to be the same. I think this is enough for us to play with. I was going to have this into a separate function, but I think that's fine. Apply the bounce force. Okay, let's try that. Okay, so it kind of works. That is not a very pretty thing. Basically, we still made it so that they can still, I guess, like go through each of these gravitational bodies. It didn't really bounce the way that I was expecting it to, but because that's because we didn't, I guess, like do like a hard stop. We could make it like more of a hard stop if we wanted to. Hmm. Um, I'm not really proud of that, so I'm just going to hide this. I know I'm going to be sharing this with you all anyway. So yeah, I'm gonna hide this and let you all some exercise to the reader if he wants to play around with this to make it so that it actually properly bounces off of the surface. For the purposes of getting through the rest of the really cool parts in this chapter, I'm going to move on. Let's actually name this to be GHW force exercise 2.13. 2.12, actually. And then let's make this 2.13. And then I'm going to duplicate this, change this into 2.12, and we're going to remove all of this bounce stuff. That way we have history. Okay, and then I'm going to move on to this next thing, move on to two-body attraction. Let's open this up and see if we can understand what's going on over here. My browser tab management is going nuts in a bad way. That's okay, we figured it out. Okay. So now we've got that going on. And we've got a choreographic solution. That sounds really cool. Let's let's actually look at the code first to see what's going on. So we've only got a single mover class instead of a tractor and a mover class, which makes sense. I think like the end body problem right now is we're treating each mover as an attractor as well. Right now, these are pretty stable, which is kind of interesting. I'm not really sure why they're in such a stable orbit if there's nothing in the middle. But I'm guessing we will figure that out when we investigate this. So we're creating a new body, okay? And then we give it an initial velocity, okay? And then there's a little bit of attraction, and then we just apply movements, okay? And then in here, let's hide these. We've seen apply force and apply updates, and updates pretty much all the time. Um, Acceleration.set. I'm not sure why. I'm guessing no, this was indeed written by Dan Schiffman. This is interesting. This is a different programming style than the way we've been doing updates so far. Because I'm pretty sure we would do updates usually. Yeah, tractor doesn't have updates. Mover does. Yeah, molt. So I'm gonna hop back over here. I'm gonna replace this with molt. Let's just see if that continues to work. Yeah, that continues to work. We're gonna do that just so that we're consistent. The stop position, the stop velocity. So it starts off with an initial velocity of 0. We apply the acceleration. Also starts off at 0, mass of 8, and then we have a proportionately scaled radius to the mass. We have the attraction function. So yes, they are indeed attracted to each other. We're making sure that whatever the value of the distance is, which is the magnitude, is never less than 5 and never more than 25. And then we do mass times the two masses. Okay, cool. So yeah, that's very similar to our attractor earlier. Um, I think this is intended to be an example that just demonstrates how um, what's it called? How elegant how a balanced two-body problem looks like. Well, I guess you have two things that are the same object, same mass. So we're gonna, in the interest of making things spicier, we're going to change it so that the bodies have different mass sizes. Let's see if that's still in perfect harmony. So I think I'm seeing them kind of move a little bit. We can track this more if we don't draw over the background. There we go. So yeah, it's not as harmonious as it was before, now that they're different masses. And actually it's more elliptical than it is a circular now, which is pretty interesting. I wonder if it's going to balance out or if it's just going to continue swinging to the left. I think it is just going to continue swinging to the left. Okay, that is really cool to look at though. Try adding a third body and experiment with initial positions and velocities. What choreographies can you achieve? Before we do that, I think it would be really cool if we actually took a look at this paper and at some of these design choreographies. I'm going to download this because I think this is really cool. So let's go ahead and look at this. Planar choreographies. That's such a cool phrase to have. Configurations and symmetries. Hmm. Well, this kind of reminds me of chemistry with the electron, I guess like um I forget what they're called. The stable electron orbit patterns. It's kind of giving me that vibe. Okay, but let's actually look at this end body choreography. A Celtic knot. Oh, wow, look at that. A perfect figure eight and a super eight. Oh, that is beautiful. Okay, I don't know that we're going to be able to get anything that choreographed unless we actually properly look at some of these videos. Um, sorry, read more into this choreography. So, as far as what it is that we do, let's just try adding in another body. Body C is equal to new body 320 um, plus 160. We'll do this a nice even 10, 10, 10. Oh, this is going to start getting messy. Because we would need to run this on. We would need to run this on both the other bodies, as well as this attracting body C, uh, body C dot, oh, body A dot attract body C. Okay, body C dot updates, body C dot show. Okay, I think that will be everything. Let's make the canvas taller. Hmm. Let's also, instead of making it 320, let's make it at, oh, that's so cool. Let's make it at 100 so that we move everything to the left. Oh my God. Oh, that is so sick. Okay. We're gonna call this GHW forces exercise 2.14. Okay. Yeah, that's really cool. Okay, I think this one is just a for n bodies. This is probably just a reformatted version of this, where it's less, um, I guess, less focused on it being pretty and choreographed, since and having more random things. Um, can you create an example? Oh, actually, okay, let's just open this up. And yeah, this is just a rescaled version or reformatted version of what we have over here. Um, because this one is it lists everything out linearly, and then this one is just properly scaled so that we can have n amount of bodies. And have them, I'm assuming, yeah, with random locations and random sizes as well. They're all mutually attracted to each other. So satisfying. Okay, so change the attraction force in example 2.9 to a repulsion force, where all the bodies are attracted to the mouse but repel one another. You know how you need to balance the relative strength of the forces and how to effectively use distance in your force calculations. Okay, so here's what we're going to do. Open this up in a new tab. I'm going to save this. This is now going to be GHW forces exercise 2.15. Oh, that's so satisfying. Okay, change it to a repulsion force. Well, I think the repulsion force is going to be the easiest thing. If we want to just make it so that they actually push each other away, instead of doing sub, we just do add. Like what we did before. So let's also have a repel. We're going to model it very closely off of the attract function right here. Let's actually just copy paste that. Mhm. Okay, so we know that the repel function does work. So then, whoops, repel other bodies. So this is every body that's not the current body. Um, so then if we wanted to make it so that they were attracted to the mouse, for example, what we can do is we can create a new vector um, wherever the mouse is. So then let's do that here. Or maybe let's do a new function, create mouse vector. And this is just going to create a new vector wherever the mouse X and mouse Y is. Okay. Well, I guess we didn't need to put it into a function. We could just put that into a variable instead. I don't know where we would need to set that up. Let's just set it up out here. Not mouse vector. Vector be equal to Boop, boop, boop. And then we also continually, I guess we don't need to instantiate it there. We could just say mouse vector is equal to create vector in that location. And then instead of the bodies being attracted to each other, why don't we just make it so that the mouse pushes? That way we don't have to rewrite that. Um, so let's move this whoop, down here. Let's actually, I want to make this we're going to have two different kinds of forces. We're going to have an attraction force, so I'm just going to call that A force. And then we're going to have a repel force. And then we're going to make it so that let's actually move this back over here. That's our force is equal to bodies J dot repel the mouse vector. Or maybe it's mouse vector dot repel bodies. Well, we don't have the repel wouldn't belong to the body. Hmm. The force. So this just gives us a force at the end. A force that's based off of where the other's position is. Where the other's position is. The other in this case is going to be just the mouse. So if the mouse is a vector, then it does indeed have position. So that should be chillin'. We don't do anything else with other inside the repel, so I believe this should be fine. To have it repel the force. Okay, well that didn't, that's, okay, so what happened here? Distance times distance. We constrain the distance, do we not? We do. Hmm. That distance. I'm assuming that the multiplication problem that we're having over here is because the strength ended up being an illegal number, but that's really weird because we have a constraint function right here to make sure that the distance isn't too weird. So I wonder if it's, I'm going to run console log on the distance over here. Let's pause this and see. Yeah, we only ever had 25. Maybe it's because we needed to have something more related to, I don't know. Okay, well, if I figure this out, I will push an update to the Discord announcements. If you want to figure that out, be my guest. I will be uploading all of the code as always, to the Discord announcements. It's just about time for me to wrap up over here. We've only got 3 minutes left, and I want to make sure that we give Iroh a chance to have some love. Um, so, um, let's see. As a recap, we were able to do some really cool things today. This being the most satisfying, of course, having the multiple movers. This was also really satisfying too. With I guess like planar. No, what was it called? It had a really sick name. Um, Planar N body choreographies. Ah, so satisfying. Um, Anyway, I will post these. Thank you so much, everybody, for tuning in, and I hope you have a fantastic day. Make sure to give Iro a hello if you're tuning in from this stream, and I hope to see you all in the very next one. We will probably be, yeah, we just about finished the forces chapter. So that means the next time we continue on the Nature of Code workshop series, we will be working on oscillations. Um, I'm not entirely sure what's going to be inside oscillations. I assume we're going to be working with springs, maybe some like wing flapping, so we can get some more accurate birds and bugs. And yeah. Ooh, I also really like where the chapter ends with getting us to think about how else we might be able to use the methods of attraction that we have discovered within this textbook. Anyway, that is it from me. I hope you all have a fantastic day, and I will see you next time. Take care, everybody.